The purpose of this video is to introduce you to the hyperbolic functions using a unit hyperbola, analogous to how the trigonometric or circular functions are defined using a unit circle. Ultimately, we want to relate these to exponential functions. Prerequisites for this video include a familiarity with trigonometric functions, exponential and logarithmic functions, as well as a little bit of integral calculus used to compute areas between curves. So we begin with a unit circle, radius 1, centered at the origin, with equation x squared plus y squared equals 1. If t is going to be the angle as measured from the positive x-axis in a counterclockwise motion, then the cosine of the angle and the sine of the angle are defined as the x and y coordinates respectively. If we then inquire about the area of the related circular sector, that area is proportional to the angle in the following way. If the area is a particular fraction of the area of the entire circle with radius 1, then the angle t must be the same fraction of 1 entire revolution, or 2 pi. And so the area is to pi, the area of the circle, as the angle t is to the angle 2 pi. If we multiply both sides by pi, we see that the area of the circular sector is half of t. So if we were to reflect this angle downward and open in both directions symmetrically and simultaneously, then the area of the entire circular sector in this picture would be t, precisely the same as the angle we originally considered. So in this way we can consider the unit circle parametrized by not an angle, but instead an area. And when t is negative, we consider the resulting area to be negative as well. It is this definition based on area that we're going to generalize or analogize with a hyperbola and define some new functions. Okay, so using the same definition with area, but now with, instead of circular sectors, you have these hyperbolic sectors. As t changes along this curve, we get different areas, and we get different x and y coordinates. The x-coordinate associated with this area is going to be called the hyperbolic cosine of t, and the y-coordinate will be the hyperbolic sine of t. And hereafter I may refer to these as cos of t and sinh of t. And as before, when t is negative, we may consider the area negative and have corresponding coordinates as needed. So as t increases, we can see the point proceed upward to the right along this hyperbola, and as t decreases, we can see it proceed downward and to the right along the bottom half of the hyperbola. The equation of this unit hyperbola is x squared minus y squared equals 1. So we want to consider the area t and use some calculus to compute that area and relate this to these coordinates cos t and sinh t. And we're going to take advantage of the symmetry of this picture and focus just on the top half in a way that looks like our original circular function picture, where the area is actually half of t. So in order to make this a little easier, we're going to end up rotating our picture. You might wonder why. If we had tried to apply some integral calculus to this region that's shaded on the picture as we see it now, ultimately we're going to have to deal with an integral of a square root of a quadratic. And that forces us to use some kind of trig substitution or something we haven't covered yet. And so in order to avoid that, we're going to rotate this entire picture 45 degrees and discuss what this implies for the resulting equations and coordinates. Okay, so we're going to rotate this entire picture, and notice I'm rotating the x-axis and the y-axis as well. So the entire picture is rotating. Okay, now after the rotation, what we're going to have is a v-axis and a u-axis. There we can see the v-axis. So the question we have is, how do the new coordinates correspond to the old coordinates? How do they depend on them? So let's take an arbitrary point xy in the plane and see what happens when we rotate it around the origin 45 degrees. If this point xy was a distance r away from the origin and was in a direction that corresponded to an angle theta, then based on our trigonometry experience, we know that we can represent that point xy as r cosine theta and r sine theta. If we were to rotate an additional 45 degrees, or pi over 4 radians, we can see that the value r, the distance from the origin, does not change. But the angle, of course, changes by exactly the amount pi over 4. Well, this cosine of a sum and sine of a sum are something we know how to compute. So let's look at u. If u is r cosine of the sum of two angles, we can use a trig identity to expand that. And since sine and cosine of pi over 4 are both 1 over radical 2, we can factor that out as well. But note that the r cosine theta and the r sine theta are nothing more than our original x and y values. Okay, and so u in particular is simply x minus y over square root of 2. So if we know a starting value for x and y for a given point, we can get the u coordinate, its new horizontal coordinate, by subtracting x minus y and dividing by square root of 2. We can do the same thing to find the v coordinate, the vertical coordinate. In this case, v is r times sine of the sum of the two angles, and we use trig identities and computation and find that the v must be x plus y over square root of 2. Alright, so let's record those two results up top so we can reference them. And let's go ahead and apply them to the points we see on the screen. So if we have a particular point cos t, sinh t, that depends on t, okay, so different values of t are going to give us different points on the hyperbola, and these have been rotated. What are the new coordinates? Well, in particular, what's the new v coordinate? So it's x plus y over square root of 2, and since the x is cos of t and the y is sinh of t, the new vertical coordinate is going to be v of t equal cos t plus sinh t over square root of 2. Down here, this particular point rotated from 1, 0, where t equals 0. And so it's just a special case where t is equal to 0. And that's where cos is 1 and sinh is 0, and so we just get 1 over radical 2. We might also wonder about the entire equation of the hyperbola. Look what happens if we multiply u and v together. We have x minus y times x plus y, which is x squared minus y squared. And we know that for the hyperbola, that's going to always equal 1. And so when we multiply u and v together, we get 1 over 2, 1/2. And so the equation of this new hyperbola after the rotation is simple. It's actually just uv equals 1/2. So now, armed with this new information, we're going to explore this area. And the first thing I want to do is actually fill in a little triangle here, because it's going to be easier to think about the area of this entire region, both the blue region we care about and the added black triangle. Now, what's really neat about this black triangle is that its area actually does not depend on t. Think about how we would compute the area of this triangle. We would do a 1/2 base times height computation. In other words, a 1/2 of a u times a v, the u and v coordinates. But we know that when we multiply u and v together for any point on this curve, we're supposed to get 1/2. And so the area of this black triangle is 1/4, no matter the value of t. And so as we move this around, the area is preserved. That's actually very convenient for us because it means we can actually divvy up this area of this region in a slightly different way. So I have the old way of slicing it and the new way of slicing it. But both of those use a triangle with a point on the curve. And so if the triangle over here that I added and the triangle here have the exact same area, then that means that the blue region before and the blue region after have the exact same area, namely t/2. And so we're almost done. t/2 must be equal to an integral that computes this area, namely the integral from v0 up to vt of the right curve minus the left curve. Well, the right curve is our hyperbola, u equals 1/2v. The left curve is u equals 0. So we have 1/2v. If we double both sides of this equation, we get t equal to the integral from v of 0 to v of t of 1/v dv. We now know that this integral gives us a natural logarithm of the absolute value v, and we can evaluate that at both of these limits of integration. Now the difference of two logarithms is equivalent to a logarithm of a fraction of those two. So we need to divide v of t by v of 0. And that's nice and easy because we're just going to be dividing out this radical 2 and be left with cos t plus sin t. Now earlier when we saw these points represented on a unit hyperbola, one of the things that should be clear to us is that cos is always larger in absolute value than sinh. Remember that the equation that describes that hyperbola is x squared minus y squared equals 1. The difference of the squares is always 1, and so y squared must be a little bit smaller than x squared, in fact always 1 smaller. And so the sinh is always going to be smaller in absolute value than the cos, and we never have to worry about the sum of these guys being negative. So the absolute values are not needed. Also, in order to get rid of the logarithm, I'm going to raise both sides as powers of e and rearrange to get e to the t is cos t plus sin t. In the same way, if I replace t with negative t, I'll get cos t minus sin t. That's reflected in the fact that the hyperbola was symmetric with respect to the x-axis. And so when I used a minus t, my cos of minus t was the same as my cos of t. But my sinh was going the very opposite direction. Okay, so where I have a plus sinh here, I have a minus sinh here. If I add these two equations, these last two equations together, and divide by 2, I'm going to cancel the sinh and get double the cos. So if I add these and divide by 2, what I get is that cos of t is simply e to the t plus e to the minus t over 2. If I instead subtract them and solve for sinh of t, I get that sinh of t is e to the t minus e to the negative t over 2. And so our conclusion here is going back to the original hyperbola, x squared minus y squared equals 1. If the area affiliated with a point is going to be t over 2, and the point has coordinates cos t and sinh t, then we know that cos t is equivalent to e to the t plus e to the negative t over 2, and sinh t is equivalent to e to the t minus e to the minus t over 2. So in our next video, we can explore what this means for derivatives of cos t and sinh t, as well as some common identities that relate them.